Astronomers are in the process of building so-called extremely large telescopes. Telescopes with diameters of 30 to 40 meters across. But is that really extreme? What about a telescope that was 100 meters across or 1,000 meters across? What about a telescope that was the size of the Earth? Remarkably, there is a trick in physics that might allow us to pull this off without ever actually building such a giant structure. Join me today as I'm going to introduce to you the concept of the Terrascope. In the autumn of 1608, master lens grinder Hans Lippershey applied for a 30-year patent in his Dutch homeland for what he called a kijker, which translates as looker. Lippershey wrote that his revolutionary instrument was for seeing things far away as if they were nearby, with a magnification of up to 3 times, a device that we would now call the telescope. Legend states that he conceived of the device whilst watching 2 children hold up 2 lenses that seemed to make a distant weather vane appear closer. After 2 other claimants for the invention came forward by Jacob Metius and Zacharias Janssen, the patent was denied on the basis that many people knew of it and it was simple to copy. Over at the University of Padua in Veneto, Italy, Galileo Galilei caught wind of this telescope concept. Within just a year, Galileo constructed his own version without ever having actually seen Lippershey's device. In fact, it didn't take Galileo long to improve upon the design and increase the magnification to a factor of 20. These early telescopes relied on a curved piece of glass, a bit like this one I'm holding here, that take distant starlight and bend it towards a focus point. Now that bending is caused by refraction. That's what happens when light passes from one medium like air into a denser medium like glass. And this has 2 benefits for our telescope. 1, it leads to magnification. Images appear larger than they really are. And 2, the very fact that this lens is larger physically than my eye means it also collects more light, and thus we get amplification. And so, when Galileo pointed his telescope towards the heavens, the age of astronomy truly began. It took Galileo just a year to discover the moons of Jupiter, which fundamentally disrupted the widespread geocentric view of the universe at the time. And since that time, we've been on this 400-year journey of building ever more powerful telescopes to reveal ever more astonishing revelations about the cosmos in which we live. If we graph the world's largest optical telescope over time, we can see a period of rapid improvement during the Renaissance. But glass lenses like this run into some problems because they bend light by different amounts depending on the color. And so you end up with these kind of rainbow halos in your images, an effect known as chromatic aberration. This was somewhat mitigated against by using lenses with very long focal lengths, such as Johannes Helvelius's 20-centimeter telescope with a whopping 150 feet focal length. And the other problem is that glass, especially as we get to very large lenses, has a significant weight to it. And that weight actually causes the glass to deform and sag under gravity. And thus astronomers began to replace these refractive lenses with mirrors, which can also be shaped into a curved manner to focus light, yet they avoid many of the pitfalls associated with the former. After this transition, progress somewhat slowed, but we still see a fairly predictable rate of telescope improvements over the centuries. But at the turn of the last century, these reflective telescopes seem to hit a similar limit as to what happened to their refractive counterparts centuries prior. Mirrors which are larger than 8 meters across, that's sort of the width of a tennis court, now have sufficient mass that they also begin to sag under their own weight, much like their refractive predecessors. Moreover, the cost to manufacture, install, and support these giant single mirrors becomes extremely expensive. And so astronomers devised a new solution by segmenting the mirror into smaller sections, which are then carefully placed together to form a single contiguous lens. As an example, the world's current largest optical telescope, the Gran Telescopio Canarias, uses 36 segmented mirrors to comprise its 10.4 meter collecting area. To account for the displaced positions of each segment, these telescopes require a sophisticated computer-controlled actuator system, which continuously modifies the angles of each segment to produce a nice, clear image. All of the extremely large telescopes planned in the coming decades intend to use segmented mirrors too, cementing this phase shift in telescope design. But these giant telescopes, like the planned 30-meter TMT or the 40-meter ELT, come with an equally giant price tag, coming in at over $1 billion each. And yet, even now, astronomers are craving yet larger telescopes, such as the 77-meter Colossus telescope or the 100-meter and aptly named Overwhelmingly Large telescope. And the reason is simple, because these telescopes could detect objects more than 1,000 times fainter than Hubble, and could even measure the chemical compositions of Earth-like planets, possibly revealing the signatures of alien life. Unfortunately, the cost of telescopes historically scales as the size of the telescope to the power of 2.5. And that means that if I say quadruple the size of my telescope, then the cost would go up by a factor of 32. Now, segmented mirror design telescopes are still a relatively new approach. It's unclear if this cost scaling works here. But even so, if we're talking about 100-meter telescopes, we have to be thinking about costs in the level of tens of billions of dollars. And this is not to mention the fact that the very best observing sites in the world, such as La Palma, Mauna Kea, and Paranal, are becoming crowded places, with Mauna Kea in particular becoming a controversial site for the planned TMT telescope. And so it's unclear whether this trend of ever larger telescopes is sustainable. Indeed, some astronomers have already referred to this as a crisis in astronomy. And so it's fair to ask, are we approaching a limit in terms of our technology as well as our economic and social will to build these ever larger machines to peer into the darkness? Are we approaching a stagnation point for telescopes? It sounds obvious, but every one of these telescope designs so far uses a manufactured lens. Whether it be the convex glass of a refractive lens, the curved metal of a reflective telescope, or the machined mirror segments for our largest observatories. No matter which one we consider, in every case, light is focused onto the instrument, be it a human eye or a modern camera, by a physical piece of hardware constructed for that very purpose. And so, the larger the telescope we want, the more hardware and associated costs we have to apply to the task. But lenses are not purely a product of our genius. They're found in nature too. A drop of water, a mammalian eye, a black hole. They all lens light without any designer behind the scenes. And as an astronomer, there's a certain appeal to thinking about natural lenses, because they don't have to be inches or meters across. They could be huge. They could be astronomical. Subscribers to the channel will perhaps recognize a familiar theme here. Over the last few years, I've become increasingly interested in the idea of using astronomical objects to achieve major technological advances. The ethos is to work with nature, not against it. And I've become increasingly convinced that other advanced civilizations, should they exist, might also adopt this philosophy. For example, in my recent paper and video, I showed that black holes could be utilized as jumping points for an interstellar highway system, providing relativistic travel without actually using any fuel, the so-called halo drive. Okay, so at this point you're probably wondering, how does this philosophy possibly translate to telescope design though? In 1979, Stanford professor von Eschliman authored a bold paper suggesting that the Sun could serve as a natural lens for future telescopes. The Sun has an unimaginable mass of 2 trillion quadrillion metric tons, which warps the fabric of space, causing nearby objects to follow curved paths. The most familiar example is, of course, the orbits of the planets, but even light is slightly curved as it passes close by the Sun, causing distant objects to appear slightly shifted away from their true location. This was famously first observed by Arthur Eddington during the 1919 solar eclipse, providing the first direct validation of Albert Einstein's recent general theory of relativity. Von Eschliman realized that anything that bends light can be used as a lens, and so Einstein's theory reveals to us that the Sun is a natural lens of gargantuan proportions. Light skimming the surface of the Sun is deflected by 1.75 arc seconds as a result of this effect. That means that 2 rays going around either side of the Sun will eventually meet at some distant focal distance. That focus will simply be the radius of the Sun divided by the deflection angle, a distance of 550 times the Earth's orbital radius. Fly a camera to that distance, block out the Sun, and when a star passes behind the solar disk, it would become bent into a ring around the rim. If you add up the total amount of light contained within this ring, it's 100 billion times more than that which you would get if the Sun were not there. In other words, the amplification is a factor of 100 billion. And so you have a ludicrous telescope, one so powerful that it could provide an image like this of an Earth-sized planet from 100 light years away. It was Italian physicist Claudio Marconi who proposed a mission to the European Space Agency in 1993 to exploit this lens, called focal. Unfortunately, the mission did not progress, with critics citing that the distance of 550 AU is simply too far. It's more than 3.5 times further out than our most distant probes are right now. Moreover, you can only really look at what is directly behind the Sun at any one time, and because this thing is so far out, its orbital period around the Sun is very slow, and thus you're pretty limited in what you can look at. Finally, the corona of the Sun is literally a hot mess to deal with, poking out of the solar disk in random ways, as anyone who's witnessed a solar eclipse can attest to. And so focal has never really been taken that seriously by NASA or any other space agency. It doesn't feature in anyone's long-term planning or future roadmaps. And so we turn back to glass, we turn back to mirrors, we turn back to segmented designs. And we limit ourselves to more modest science, more realistic goals, more proven technologies. Well, bollocks to that. Okay, so fine, maybe the Sun is out of our current reach, but the concept is brilliant. What if we could replace the Sun with a different natural lens, a nearby astronomical object which could serve as an intermediate stepping stone for us to hone our lensing skills and yet at the same time achieve colossal lensing capabilities? Something closer to home. At first, the idea of using the Earth as a natural lens seems ridiculous. After all, the Earth is 300,000 times less massive than the Sun, and so Einstein's theory tells us that it should barely deflect light at all. But gravity is not the only game in town when it comes to bending light. 13 years ago, I wrote this: The Green Flash and the Green Ring. This is my master's thesis during my time at Cambridge University. It was a necessary part of my degree to undertake some research, and so I chose a subject that was as close to planets as I could find. It was Dr. Peter Duffett-Smith, my advisor, who offered me a project to try and explain the green flash phenomenon. Now this is a well-known effect, and I bet many of you have even seen it. So I think he offered this project every year. It wasn't supposed to lead to an actual publication or something, but rather just give a taste of what research was like. When the sun is about to set, it's actually already half a degree below the horizon, but light is bent through the atmosphere due to refraction. Refraction, which is, remember, the very same effect that was used in the oldest telescope designs. Now, blue light refracts more than green, and green light more than red, and so in principle, the very last bit of light that you see coming off the sun should be blue light. But because of scattering in the Earth's atmosphere, blue light is essentially attenuated completely, and thus the only little bit of light that you have a chance of seeing is the green, hence the name green flash. So I went ahead and came up with a simple model to describe the atmosphere, wrote some software for doing the simulations, and I calculated the deflection of light and these scattering effects. As a personal side note, I have to say this was a formative experience for me. I got a real kick out of doing some research like this, and it gave me confidence that yeah, I could problem solve, I could do research, and maybe this could be a career for me after I graduate. But towards the final section of my thesis, I also realized that one could potentially see a green flash from space. In fact, if the sun were directly behind the Earth and you were located, as I calculated it back then, 2/3 the distance between the Earth and the Moon, then you could see a green ring around the Earth. I even hacked together this visualization of what this green ring might even look like by using Photoshop and an image of a solar eclipse. But I mean, this was an intellectual curiosity, and my advisor broadly agreed with that. But I remember one thing that he said to me was that he'd never seen anybody approach the problem quite in this way before, after years of offering this project, and something about that stuck with me. And so I think in the back of my mind, I always thought maybe one day I should turn back to this and investigate it further, see if there was anything to this. Many years later, during my time at Harvard University as a Sagan postdoc, I heard about the focal mission for the first time, and I was really blown away by it. And I remember that I immediately made the connection back to my master's thesis, and I realized that maybe one could use the Earth as a refractive lens instead of the sun as a gravitational lens. But I was a postdoc back then. I mean, I did not have job security. I was on a short-term contract, and being a postdoc is kind of tough. You have to spit out lots of papers on reputable science, and frankly, my main project was already risky enough. I was looking for exomoons, for goodness sake. So I just didn't feel comfortable turning to this project and writing it up. I thought it was too risky to do. But I told myself, as before, one day I'll come back to this. One day when I have a faculty job, I'll turn back to this and try and crack this problem. Well, last summer I realized that I'd been at Columbia as a faculty member for a couple of years now, and really I could afford to finally revisit this problem, to take a risk. And so for the last 12 months I've been working diligently on this problem, trying to figure out if this crazy idea from my youth had any merit to it. And so, 13 years in the making, I'm delighted to say that my paper on this subject has now been accepted for publication in a peer-reviewed journal. And as regular subscribers of the channel will know, I'm fond of giving my projects punchy names, and so I'm delighted to introduce you today to the Terrascope. Imagine a distant star setting on the horizon. Light from that star enters the Earth's atmosphere and deflects by half a degree. It skims the surface, then makes its way back out of the atmosphere, giving another half a degree bend. So 1 degree in total. Light from that same star will also shine upon the opposite hemisphere, and the two rays will converge together at a distance given by the radius of the Earth divided by 1 degree. So that's a distance just interior to the orbit of the Moon. This is a focus point. If the ray were any closer to the Earth, it would strike the surface and thus be lost. If the ray were a bit higher in altitude, then it would bend a little bit less, since the atmosphere is thinner as altitude increases. So this means that not only do you get a focus for surface skimming rays, you will also get a focus at every point more distant than that too. In other words, you have a focal line. Now the immediate problem with this is that a ray traveling so close to the surface will surely be lost along the way. It might intercept clouds or mountains or even buildings, or frankly even just be absorbed by the very thick atmosphere through which it has traversed. And so it's fairly straightforward to convince yourself that a surface skimming terrascope is not going to work. So let's consider higher altitude rays. A ray with an altitude of about 1 kilometer will focus onto the surface of the moon, which would obviously be a very interesting place to put a telescope. But sadly, scattering and extinction effects at 1 kilometer altitude are still rather severe. Extinction is very dependent on the color or wavelength of light that you're looking at. So here you can see the amplification of the terrascope assuming a 1 meter detector as a function of the wavelength. Those different colored lines correspond to different climatic conditions on Earth, but they all show rather flat responses except in the gray banded regions. Those regions are known as atmospheric windows, where the Earth's atmosphere gives us a bit of a break and stops being so opaque. So, a near-infrared detector on the Moon could perhaps achieve amplifications of around 10 to 40,000 according to my calculations. Now all of this sounds very promising, but I haven't talked about clouds yet. Clouds cover 3/4 of the Earth and can block out almost all of the light that we're trying to use in our terrascope. So if we want the terrascope to work, then we're going to have to use rays which actually travel above the clouds themselves. But how high can we really go? Because the higher in altitude we go, the less atmosphere there is, the less refraction we have, and thus the focus point moves out to potentially an unusable distance. In my paper, I suggest a realistic useful distance for lensing is the region of stable orbits around the Earth, known as the Hill sphere. By placing a detector here some 4 times further out than the Moon's distance, lensed rays would have skimmed the Earth at an altitude of 14 kilometers. That's enough to have missed the vast majority of clouds. Using high-resolution cloud maps from satellite reconnaissance, I estimate that clouds would lead to a loss of 8% of starlight in this configuration. That's small enough that clouds no longer ruin the terrascope concept. Moreover, extinction effects also dramatically drop, and now you can see that most of the infrared spectrum becomes usable for lensing. So our destination is just 1 Hill radius away from us, which is actually the separation that many of our new space telescopes are going to, such as the upcoming James Webb Space Telescope. Once out here, we'd want to block out the disk of the Earth, and probably the lower 14 kilometers of non-usable atmosphere too, in order to reduce airglow from the lower atmosphere. Now, whenever a star, a planet, an asteroid passes behind the Earth, we will get a chance to see its light lens around the Earth, and that lensing should last for about a day, giving amplifications on axis of 45,000. In the paper, I conservatively halved that number to account for possible losses as one side of the Earth is in sunlight. So that gives you 22,500 for your amplification. That's a little bit of a difficult number to parse what that really means, so another way of thinking about it is that it's turning your 1 meter detector into a telescope with the effective collecting power of a 150 meter telescope. So that would mean that you're moving from, say, tens of parts per million photometry to a few parts per billion photometry, the kind of level where you can start to detect exotopography, biosignatures, and very faint sources on the other side of the universe. A 150 meter space-based telescope would cost a ridiculous amount of money to build. For example, the 6.5 meter James Webb Space Telescope costs about $10 billion. But a 1 meter detector using the Terrascope effect could cheat its way to 150 meters, achieving the same power at a tiny fraction of the cost. Now, there's no such thing as a free lunch, and so there are definitely some limitations with this Terrascope idea, don't get me wrong. One of the biggest limitations is that you can only look at whatever happens to be behind the Earth. But the alignment doesn't have to be exact. Actually, it could be offset by about an Earth diameter and you still get plenty of lensing. You can see here an animation I made of how the lensed ring of light appears as a star passes behind the Earth. You actually get even higher amplifications when the source is offset by about an Earth radius, and that's due to the large oval-shaped rim that forms at those times. One could imagine using a fleet of small detectors around the Hill sphere of the Earth to enable pointing control across the sky. So all in all, I'm very excited about the prospects of a Terrascope system, and one can even imagine trying to use this on other planets too, such as Jupiter and having a Jovascope. But there are plenty of things to be figured out before we could ever go and build one of these things. For instance, what is the real-world performance of this system when you have atmospheric turbulence and shear effects within the atmosphere? How easily can you distinguish the lensed photons from the background contaminant sources in your image? And what kind of occulter do you need to precisely remove light from the Earth? Those concerns and more that you can think of, I'm sure, are all very valid reasons to have some degree of skepticism when you think about this Terrascope system. And so I'm not going to sit here and tell you that this is some kind of silver bullet to astronomy or something. But hopefully I've convinced you that this is an exciting enough concept that it deserves our research attention. And if my paper succeeds in doing that, then I would consider it to be a success. Let me just finish by adding a personal note. This project was 13 years in the making for me, and that's a timescale which is long enough that this was in grave jeopardy of never coming to fruition. And I bet many of you could probably relate to that feeling of having had some idea or dream from your youth that bit by bit, piece by piece was dismantled through the advice of others, was relegated to the wasteland of lost ambitions. And you tell yourself that one day you'll come back to it, one day you'll pick it up and dust off that dream, but it slips, week after week, month after month, year after year. I am so privileged to have had the intellectual space, the job security, the financial freedom to have taken a risk like this. I could afford to put the regular bread on the table work to the side in order to focus on this project. And it means a great deal to me to finish what I started all those years ago. But I have to say, I have a big regret, and that's that I didn't do this sooner, that I should have been a better role model to you guys. Look, if you have a dream or a passion or an idea, don't do what I did. Don't wait a decade and a half to pursue it. I regret that. I mean, you might not even have that much time left. And I know it sounds cheesy and corny, but in the context of this story, I feel like I have to say this. If you have something you want to do, this is it, guys. This should have a sense of urgency. This is your moment, and this is your time. So I don't know where this whole Terrascope thing will go, but I'm certainly glad that I finished the damn thing. And if you like these kinds of ideas, then stay tuned, because we've got a lot more coming down the pipeline. So make sure you tune in and subscribe to the Cool Worlds channel, and you can join us for that journey. So if you've made it this far, then let me say thank you so much for your valuable time. But do yourself a favor and turn off YouTube for a little bit. I know the algorithm's going to hate me for saying that, but give yourself license to think about one of those crazy ideas in the back of your head, one of those wild ideas from your youth, and maybe pick it up, dust it off, and see where it takes you. Until the next video, stay thoughtful and stay curious.